Hello everybody and welcome to Omak, Washington, Okanogan Valley, Northern Washington. That's Jerome Lesemann, Vancouver Island University, flying a drone. Why are we here? In the last hour of daylight? Earlier today, so you're down here for how long?
About a week.
About a week.
About a week. A return of sorts after many delays, some related to border closures and others just, work life and everything else. So
exactly.
yeah, I returned to an area that I've been through before and worked a bit in, but not as much as could be done, and certainly lots of open questions that are interesting to look at and think about. So
excellent. Well, this is where we start. And there's a reason you've taken us here first. I mean, you're just kind of exploring, right? You don't have a bunch of details that you've worked out yet.
No, not at all.
Yeah.
I have a series of working hypotheses,
yes.
Let's put it that way.
Yes.
But this is still very much kind of reconnaissance and exploratory and
okay.
Trying to get the lay of the land of sorts.
This is a public road, and so I'll put the GPS location for this spot if you want to come out and see. It's like, what the hell? Why would I come out and look at a bunch of tires out in the middle of a cow pasture? Well, you got something in your... Look at this snazzy van, by the way. You've been re-energized for a number of reasons, but one of them is LiDAR coverage that's out here now.
Yeah. The state of Washington flew LiDAR in a number of key places in the state. We also have now LiDAR in British Columbia, so there's a nice connection or match there. And the data that LiDAR are astounding for geomorphology. It just gives you, it's like you're myopic and then suddenly you get a pair of glasses that suddenly allows you to see the world completely differently. It's incredible what you see in terms of detail and the ability to digitally work with these files and zoom in, zoom out, move around the whole landscape, and just see landforms in the way that you can't really see otherwise unless you do some really detailed and painstaking air photo mapping work, which takes a long time, requires a lot of photos, but the LiDAR is so accessible and so easy to use. It's amazing.
Okay, so we can say that sitting in an office, but it's one step further to say, oh my God, I got to go out and see this for real. And this is your spot. This is one of your spots that you got intrigued by. Let's see what it looks like on the LiDAR to get you out here. So we're going to duck into this beautiful van, I think, to get a little darker so we can see this image. Let's give that a try. Is that what I think they are?
Yeah, if you're thinking giant current ripples, that's what they sure look like.
So did someone tip you off that the LiDAR showed these ripples, or were you truly like scrolling around on your office computer or something and you're like, hold the phone, what do we got?
A combination. I think it's a lot of cruising around the LiDAR data.
Yeah.
And around the same time, and it may have been Sky that pointed them out or sent me an image, Sky Cooley, we were talking to you last week, said, hey, have you seen these? And there they are. I mean, that's they sure. I mean, I don't think at this point there's much doubt that that's what they are.
Okay.
I mean, in some places they're a little bit more ambiguous in terms of shape, but here they're pretty convincingly large-scale bed forms. One of the challenges with large bed forms like these is that they're so large that sometimes it's difficult to see the actual repetition of the pattern that characterizes the bed forms. But from this vantage point here, it's pretty good. So there's some troughs for the cattle, and they're sitting on a bit of a ridge. And if you're moving to the right, it dips down to a low. Then there's these red boxes on another ridge, another low, and then there's a fence where there's a lone cow on the top of the next ridge. So these are three of the many undulations that we could see on the LiDAR. Diameter that we can measure, we can do this off LiDAR. Here they're about 150 feet apart in terms of chord length, so crest to crest or trough to trough. So, red box to cow on the hill, that's about 150 feet. And then we also think about the amplitude of the bed forms.
Okay.
So how high they are in relation to the low spot in between. So here we're dealing with somewhere, again, 5-6 feet high, something like that.
Okay.
There's a bit of a less cover. I don't know how much the cows have moved it around, so they're estimates. Okay, they're just back of the envelope
I'm with you.
type of stuff.
I'm with you.
So 150 feet chord length, 5 feet high. With those dimensions, we're looking at probably velocities on the order of about 30 feet per second to move the material. If we've got a velocity, the depth, this is another parameter that Vic Baker allows us to sort of derive from some of the graphs. The depth is somewhere on the order of about 50 feet deep, the water, the flow above our heads.
Okay.
Oh, but to put that into perspective, that is not mega flood scale discharge.
Okay.
Mega flood scale discharge, by definition, is 10 to the 6
Mhm.
meters cubed per second magnitude. Or
Mhm.
so we're certainly looking at something smaller than the main or the peak discharges that are inferred for some parts of the Channel Scablands,
Yeah.
no doubt. But 10 to the 5 is nothing to sneeze at. 30 feet deep, moving at 30 feet per second, that's fairly substantial flows moving through this area. And so they may not be on the scale of what is moving, at the peak, moving through the Scablands, but it potentially is significant nonetheless in terms of, if you ask yourself the same questions as you ask yourself in the Scablands, if you have that much water moving through, where does it come from? What mechanism are we producing water, releasing water to generate these velocities, to create these bed forms in this particular location?
So that's what you're doing this week. I mean,
Part of it.
You're on your summer vacation. School's done.
Yeah.
You're down here for fun, I guess, but
Yeah.
it's part of your gig to like.
It's part of my gig. It's
keep
part of
learning
the
new stuff.
research interest, so it's a way of continuing that.
Yes.
And it happens, I can't do it during the regular school term just because of timing. And
Yes.
so on the shoulder season, between my kids still being in school and the students, university students being done, there's a window there where
Sweet
you
window.
can do that.
That's
so,
right.
Yeah. So this is one of the questions that is intriguing. It is fitting into, or we're trying to work into, and I say we because this is something that Sky Cooley and I are
Okay.
planning on working on together, but it's part of the story somehow.
Okay, so yeah, we could be in a prettier spot, but before we cut the camera here and go to another attractive location, those look across the way, are those Ice Age features?
Yeah, you mean on the other side of the valley, like
Yeah.
against the bedrock wall. Yeah, so that feature across is another reason why I'm here this week. And it's the fact that Okanogan Valley in general, whether you're in Canada or whether you're on the US side of it, but especially on the US side, the valley is characterized by enormous, extensive terraces. That's what people have called them.
Yeah.
The most well-known and the largest is what people have called the Great Terrace.
Yeah.
It's at the confluence of the Okanogan and the Columbia.
Okay.
But there are similar features all the way along the axis of the valley as you move back northward.
Huh.
And they're prominent on the hillsides. And sometimes they extend quite a ways into the valley. Sometimes they seem to be truncated. So the ones across seem to be a little bit more truncated. But wherever you look on this landscape, it's fairly easy to recognize because there's bedrock exposed, so steep slopes are bedrock, and
Yeah.
there's a very obvious and very sudden break in slope, and that becomes one of these benches, or colloquially they're called flats around here.
Okay.
Brewster Flats and
Oh,
Pogue
yeah.
Flats and Sand Flats.
Yeah.
But they are these valley side terraces, and we can talk later about whether that's the right term or not.
Sure.
And we're standing on one, or a portion of one, but the upper flat surface for us is above the cows. It's that line on the horizon.
Okay.
And later, as we drive away from here, what we've done is we've sort of driven off that upper surface. The Omak Airport is on that surface.
Okay.
We've driven off the edge of that little surface, and we've moved onto a surface that's been eroded, presumably where these big bed forms have been created. So we've kind of incised into an upper terrace. And we see that likely, I'm jumping a bit ahead in terms of interpretations, but the thinking is that if we've incised, and as the process of incising that upper bench, the flows were sufficiently energetic to be moving the material and producing these bed forms. So if you just spin around, you can see another fantastic landscape, but the road follows three humps. You can see them in the distance, right? So the road is just going over the crests of these bed forms.
Giant current ripples.
Yeah. Not as big as West Bar. Let's
No?
be clear.
Yeah, okay.
West Bar, they're what? They're 25 feet high or 20 some feet high.
Sure.
So these are certainly smaller, but not insignificant.
Are we looking straight north?
We're looking, yeah, almost straight north.
Okay, what's the plan?
So we're gonna head up the north on the up the valley, up, down, north, and we're gonna cross a bridge at a place called Riverside, so we can go to the east side of the Okanogan River,
Okay.
and then we're gonna head up. So we're gonna make our way upstream
Okay.
in a tributary valley to the main stem Okanogan, and
Oh, so you got all this LiDAR
I'll
printed out
just
on
turn
these
around
sheets.
for you.
Yeah,
Yeah, these are my scribble sheets,
Nice.
so I can just sort of draw things
Oh,
around.
cool.
So if that comes through well,
I think
we're
it
going to
does
come
even
through on
better.
the highway here, and we're going to go up this canyon. And I'm saying canyon because this general sort of morphology is very similar to what I've seen on the Canadian side of the Okanagan. So it's not entirely unknown or new. I do have some reference points for some of the landforms. So
you didn't stumble into this area for the first time.
No.
You've been studying and publishing up there forever.
So what we see north, and I think we can sort of see some of that is on the LiDAR, is that commonly when you enter a tributary, there's a major canyon. There's a bedrock canyon,
Okay.
and either the road goes above it or through it, depending on the size of it. But I think we're going to see that, and we're going up a creek called Tunk Creek, and we're interested in having a look at some landforms. They look like large fans that are perched up high on the sides of the valley.
Do you have the sheet that has our cow ripples right here?
No, not on the paper,
Oh, you
not
don't?
printed out. I only have it
Okay.
on the screen that we were looking at.
Okay, cool.
But we might be able to
All right.
still see it. There's a bit of shade now. Maybe that works
Yeah,
better.
let's give it another try.
Yeah.
We've got all sorts of stuff here. I love it.
And I can even zoom it out a bit. You see where they lie in relation
Unreal.
to. So this surface here is one of these big flats. It's one of the highest surfaces in the valley. You can see there's
Yeah.
channels on it.
Yeah.
And these bed forms are on a lower surface that is not quite as flat. So it's been trimmed or eroded to some degree. So we've incised partially into the higher upper surface. And then there's yet another round of incision at some time, probably by the Okanogan River, to produce this escarpment.
So this is 97.
97 is right
This-
there,
that guy.
that line. And that train of ripples we were looking at is most convincing where the blue dot is. But you see that there may be hints of it continuing further south.
Mm.
But it's the pattern may be affected by kettles. Or there's some sort of irregular topography that might be associated with blocks of ice that would have been buried in the sediment and then collapsing. So it potentially obscures a bit of the bed forms if they're there. I'm not sure. It's not very convincing.
I don't want to overstate it, but like up until last year, nobody knew those giant current ripples are here.
Until I think the LiDAR
Yeah, but
was available, and then
even
we
the
started
LiDAR,
looking.
nobody really has
2 years
noticed
ago.
it, written it, or
No,
done
it's
anything with it.
in the last few years. No, before then, no.
Okay, we're in on the ground floor. Love it.
We are. I mean, interesting things that pop out. Yeah, we'll see.
We're about to drive up and over a few crests right here. This is so cool.
Me here.
Look at this place.
It's a spectacular day today. Turned out gray, but wow.
So you've got some LiDAR imagery here. Oh, look at this muffler boy. Making time. We're near Tunk Mountain, east of Riverside, Washington. And maybe could we start with the imagery that
Let's do that.
attracted you to this area?
Sure.
Some breezes picked up at just the wrong time, but maybe we can.
Oh, that just makes it interesting.
There you go. So it's not like you're giving us this lecture professor in this place that you know well, right? This is yet another place that you're just.
I've never been here.
Never been.
Let's just call it what it is. I've never been here.
I love it.
I've never been here,
And I
but
haven't either.
but I have in my mind.
Yes, you
As
do.
in, I have looked at this LiDAR for a fair amount of time to
Yeah.
try to recognize and map landforms, which give me a bit of a clue to what I might see on the ground. This particular linear feature, which is a negative feature. In other words, it's like a channel or it's a depression. It's a linear depression.
Right through the frickin' ridge.
Yeah, and this is what's notable about it, is that this is a topographic divide to the next valley to the north. So we climb up to this divide and we would continue down, losing elevation to the floor of the next valley. And crossing that divide is this singular, very deep, prominent channel. If you turn your camera, it's right there. That's the gap that I'm pointing to in the distance.
So we're looking north, more or less.
Yeah, more or less north.
And why is that notch there? And beyond the notch, I'm just going to kind of roll with it here, Jerome.
Yeah, go for it. Lots of terraces or levels anyways, flat.
God, yes.
You can see one in the foreground. There's one that seems to be a little bit inset below. In other words, there's a bit of a step down, like there's a riser, much like a terrace, and there's another surface. And that surface continues, and we see it going, it's this prominent, broad area in the distance.
Let me see.
There's not much sediment on those bedrock uplands here. Across the whole ridge, we see that pattern on the LiDAR itself. There are some textural appearances we can see, but even when here on the ground looking across the valley, we can see that it's just basically outcrop and no real sediment cover. And the sediment really starts at some lower elevation where it's characterized by these really flat, low relief and extensive surfaces. And in some cases, probably terraces is appropriate, as in we've incised, we think of it as a surface of deposition of sediment, and then we've incised through it and produced another surface of deposition. So this insetting or this downstepping like a stair step, we see it really well here. There's a short, small surface at the top, and then we step down where the road is. You can see the little dirt road, the two-track road.
Right.
It's on a surface for a while, and then the main road that we've driven up is even lower than that. And this is where the LiDAR really becomes helpful, because that very extensive surface we see extending in the distance is the one that we can see on the LiDAR map. I'll try not to cast a shadow.
This is great.
But it's going to be most likely this large surface. I think it's this one here. And the small one that we see is the one that's just directly in front of us. Okay, so we have the stair step. There's one, and then there's a second surface. And we're looking at it from this vantage point across.
Do you see these features up in BC?
Yeah, sometimes. I mean, one of the open questions is exactly what those features are. We can see their morphology. There's these flat surfaces.
I mean, it's like a sore thumb. It's
Yeah,
like
it
just
sticks out.
pops right out.
And it's clearly associated somehow with this notch and this incision. It's called an incision. I mean, one of the questions that I'd love to be able to tell you or answer is it a delta, or is it more like an alluvial fan? The morphology is interesting here because it has a very steep front and it seems to end very abruptly. This arcuate, rounded front that we see on the LiDAR. Typically in an alluvial fan, there's a fairly steady grade to the fan, to the valley bottom, to some low point. This ends very abruptly, which is not unlike what you see on coarse-grained deltas that have the foreset component of the delta that can remain as a major break and slope or as a major step. So morphologically, that's one option. The answer to this would be to see the internal architecture, but I don't know if that's even going to be possible. We'd have to be really lucky to get an exposure where we can see that. As we see a little bit here, is that there's been multiple episodes of this building. In other words, what I mean by that is every time we have a step or a terrace and we step down, the implication is that we've eroded down and removed some material and redeposited the material again on at a lower elevation. So think of it this way, one surface here that may have been more extensive, incised to build this second one, incised to build another one down here. So there's a potential for sort of this sequential building. And if that's the case, again, as a working hypothesis, maybe the location and the elevation of these surfaces and the deposition is actually controlled by a water level, like a lake. That's certainly a pattern that we would see in many places where lake level controls the incision and the deposition of sediment. But it raises all sorts of other interesting questions, which is, what is the lake doing near the topographic divide of a side tributary? We're really, really high up in this valley. We're kind of on the regional high points, not in the valley bottom, and we're inferring potential for standing water if that's in fact what these record. Here it is. So, pretty sizable clast,
Sure.
well-rounded.
Yeah.
Not everything is this rounded, so some of them may be derived locally, others have been transported more.
Okay.
But this is roughly the caliber of the material that we see in these surfaces. So these are very coarse gravel deposits. They seem to have a sandy matrix as well, so there's a mixture of material. We don't really have a clear exposure to really see what's in them. We're going from what's on the surface, but even as we drove up, we could see that there's boulders dotting the surface and the slope, the risers of these different terraces.
Now, we don't know the age of these beautiful flats over there, but I think everybody from this vantage point can see we have at least two of these major terraces. Now, this is similar to something called the Great Terrace, right?
Yeah, it's similar in some respects. It's different. Let's start with the difference. It's different in its size. That's the big thing.
Okay.
It's probably a little bit different in the caliber of the material that's within it, but not that much, I would venture. I think the Great Terrace does have a lot of gravel and sand. I kind of like to think of these as mini Great Terraces. In other words, they might be recording very similar processes and environments of deposition, but they are at different elevations from the Great Terrace.
Well, full disclosure, we've been sitting here for a half an hour talking. I finally said, I got to turn the camera back on, Jerome, because I love this Great Terrace discussion. What is the Great Terrace? Where can people see it? And which level interests you the most?
Okay, so the Great Terrace is at the confluence of the Okanogan and the Columbia.
Okay.
It's right around the town of Brewster.
Yep.
Or Mons as well as part of it. People are familiar with that. And it's on the west side of Okanogan Valley, but it really kind of rounds the corner of the Okanogan to the Columbia.
Yeah.
And it's well known largely because it's so prominent, and then and extensive, and it's been mapped for a long time. I think Israel Russell is one of the first people to identify it and recognize its significance. Though the interpretation of the Great Terrace vary a lot. Some people recognize deltaic structures and some outcrops. Other people have recognized more planar gravel bedding that's more consistent with a fluvial terrace. And I'm not sure if both are not compatible, but that surface has attracted interest mostly because of its size. Now, some people correlate the surface of the Great Terrace further downstream towards Chelan. So there are remnants of flats that look very much like these in most of the coulees and steep tributaries that drain the west side of the Columbia Valley.
Yeah.
And they've built these perched or elevated flat surfaces or flats that are coarse gravel sand composition. And so some people have correlated that surface. So this is an elevation correlation, saying, okay, there's a continuous surface that at one point existed.
It's not perfectly flat. It slopes a bit to the south.
It slopes a bit.
Yeah.
It's not we say flat, but
yeah, right.
I mean, flat. It's flat as in it's not bumpy. It's featureless. It's not horizontal. Let's not confuse the two things.
Right.
It has a slope, but it has very little relief on that surface. But the Great Terrace also continues to some extent northward along Okanogan Valley, and so my interest in that Great Terrace is, and any of these flats that are on the sides of the Okanogan Valley, is really the highest surface because it's probably the oldest. And in many ways, there has been incision and reworking. But what I think is important is that the initial highest surface is the one that supplies a portion of the material that ends up in the lower flats.
Oh, right.
Okay, so we build the first flat, and then we incise and we kind of cannibalize some of that material from the first flat, and then we use it to build the lower one, presumably at a lower, grading or the water moving to a lower base level.
So it's scooping, it's recycling of that material.
That's the way to think about it. It's recycling its own sediment. And certainly there can be an input of newer material, but the fact that we have a terrace tells us that there's been some amount of incision. In other words, there's been erosion and recycling.
Even to make the first one, the oldest one? Like that's the one that interests you the most. That's the most controversial.
Maybe not the first one.
Right.
It's in the incision of the subsequent terraces, because often we'll see these flights of terraces, these steps. But the first one is sort of the main one. When that initial highest surface, the flat, builds out into the Okanogan Valley, and that big opening of the Okanogan Valley,
right.
Is it building clear across the valley?
Right.
In other words, is it really creating basically a new valley bottom so that we could correlate those surfaces from east side to west side and vice versa?
Yeah.
Or is it building against ice, because there's some amount of ice in the valley?
Mm.
And that's certainly something that the prevailing thought on the pattern of deglaciation might suggest, that there's remnant ice because that's where it was really thick.
Mm-hmm.
And so it's building against ice. That would fit into the Kame terrace model.
Yeah.
Or is it building into a body of water that is somehow confined or constrained by ice? Something along those lines, right? So we're kind of splitting hairs on the depositional environments, but ultimately we're kind of getting to those questions.
Well, the storyline is there's no major ice age floodwater coming down this valley. Why not? There's no basalt here.
There's no basalt.
Okay, so we're out of the basalt, so we're not expecting to find coulees or dry falls or anything like that.
Well, we have coulees. I mean, there are bedrock channels that are called coulees. They just don't look like the Scabland coulees.
Okay.
They have different shape morphology because the bedrock's different in part. But it also raises the question as to whether or not there are in fact possible floods of meltwater that come down the Okanogan. Down being south, like south to the Columbia River.
Yes. I mean, I think you know what I'm after here, Jerome.
I know what you're
I'm like,
after.
there's some stuff down south that is getting harder and harder to believe it's all water from Montana. We're looking right up the barrel of the gun. We have a huge Okanogan ice sheet. We've got features that you were showing me in October where there's no glacial till, everything's stripped off, basically a big fire hose, pressure washer washing all this stuff away. And isn't this an obvious place? So what could be documented here by you or somebody else to tell us, yeah, we do have major ice age floodwater coming down this drainage, even though it's not obvious to most of us?
Okay, so as you said, it's not obvious to most, and it's not necessarily agreed upon. Actually, nowhere near that. But
right.
So the arguments that have been made for water coming out of the Okanogan, there's kind of two stories that are related to each other.
Good.
One is that a portion of water coming from the Okanogan happens under the ice sheet. So it's flow of water under the ice, subglacial flow. The evidence for this, well, there's multiple lines of evidence that we've put together to make that case. One involves what we call tunnel valleys.
Okay.
Tunnel valleys are channels that we tend to observe or find in glaciated environments, not in areas that have not been affected by ice. And the diagnostic feature of a tunnel valley is the fact that if you move along the profile of a channel, they can go uphill, which you can't do with regular subaerial river flow, obviously, because we don't get water moving uphill. So the implication is that water is under pressure, and it's under pressure because it's under the ice. So we drive water over topographic highs and in nice continuous channels cut into bedrock. Yes, sometimes those bedrock channels can have a structural, imprint or a pre-existing structural weakness that we exploit, but it doesn't remove the fact that we create erosion along that channel. And they're often free of sediment along the entire length of the channel. They're free of sediment downflow of the channel, so it's not simply just a trickle of a stream moving down the gradient and depositing sediment. It's just flushing and moving anything that it's been mobilizing beyond the location of where the channel occurs. So there's a number of these. There's some that occur right at the confluence with the Columbia River. Omak Lake is an area that we've interpreted as being a potential tunnel valley. And there's lots in the Okanogan Valley north of the border around Penticton and Kelowna. And we had also made that case using some of the characteristics of the fill of the valley, the sediment fill of Okanogan Valley, which seems to be very young and mostly sand and gravel. So that's one part of the story, or one line of argument to say that there might be some catastrophic floods down, flowing south along Okanogan Valley.
Before you move
That's
on to
part
the
one.
other one, have you called this a tunnel valley on the U.S. side before?
Not this stretch of valley.
Not this stretch.
Because it doesn't have that diagnostic uphill or convex or concave long profile. But it doesn't mean, if it doesn't have it, it doesn't mean that it can't be utilized under an ice sheet as a conduit.
Okay.
It just means that we can't differentiate it from a regular subaerial river versus that of a channel created under ice.
Because just to
So
follow,
it doesn't mean that it cannot be.
Right.
It's just that doesn't have that diagnostic feature that really points to that origin.
because if we keep going in a raft down here, the Okanogan, we eventually join the Columbia. We keep going past Chelan, Wenatchee. We keep going. We're not having to climb at all.
No.
There's no reason to get into the Tunnel Valley thing per se.
No, and we wouldn't expect to see it around Chelan or along the Columbia further south because we're beyond the ice margin. So once we're beyond the ice margin, we do not have that additional pressure component that can drive water up, up an adverse gradient.
Good point. Okay, interrupted you. The other
No problem.
thought.
The other part of that story, or the other element, is that perhaps there are large quantities of water flowing down the Okanogan. Are they catastrophic? Who knows? Are they ice age floods? Well, they would be around the timing. But that are not subglacial, but they're related to the retreat in whatever configuration and pattern that happens of the southern margin of the Cordilleran ice sheet.
Yeah.
So I think that implies that perhaps those discharges would be smaller than those that happen subglacially, maybe.
Yeah.
That's a bit of just a guess or a thought more than anything. But the lines of evidence then, we basically need another set of data to sort of make that case.
Yes.
We really have to sort of separate those two stories potentially.
Right.
My standpoint is that I cannot understand how we wouldn't have water flowing along the Okanogan during deglaciation, because the margin of the Okanogan lobe on the Waterville Plateau is, 200 kilometers, something like that, that way.
Right.
And the drainage divide that goes into the Fraser River is another 250 or some kilometers that way. So there's along this portion of the Okanogan, there's about 400 kilometers of the ice margin where the natural direction of flow when the ice sheet is decaying is to the south. So the question for me is not whether or not there's meltwater during decay of the ice sheet that flows in the Okanogan. I think it
had to come through here.
I don't know where else it would go. So it has to go in this direction.
Okay.
The real question, and maybe we're sort of barking up the wrong tree sometimes.
Well, let's bark.
The real question is sort of what's the configuration of that flow of meltwater? By that I mean, are we melting the ice sheet slowly, gradually, and it's really just a trickle of maybe a proto-Okanogan river that might be a bit bigger than what it is today, but it's not an enormous, sudden, kind of episodic event?
Yeah.
Or is it, and perhaps in combination with that, are there cases or times when we store and pond water during retreat and we release it suddenly? And that those two styles or those two sets of processes are totally compatible with each other.
Yes.
We look at decaying glaciers today in Alaska, in Iceland, and all sorts of places, and temporary ponding of water is kind of a normal thing.
Yeah.
And temporary ponding is just that, temporary, which means that there has to be a time when that pond drains.
Is this one of those flats? Are we looking at the guts of one of these flats?
Exactly. So there's the power lines are on one of the flats.
Okay.
They continue across. There's another flat. It's not the highest surface.
Okay.
Here you see there's a bit of a step down, so it's one of these slightly lower ones, and then the highest flat is where the pylon is, at the top. This pile of sediment very likely is part of one of the higher surfaces, and then we subsequently incise and remove a portion of it, but the guts of it are really part of the initial deposition that builds the highest surface.
So are these Canadian rocks?
That's a good question. I think there's a mixture of things. I'm not sure how much. I think we'd be hard pressed to be able to tell them apart because this, everything to our east here, to the east, is the Okanogan Dome Metamorphic Core Complex, and so there's going to be probably some similarities in terms of sourcing or lithologies. I'm sure we can find differences, but
you assume that many of these flats have guts that look like this.
yeah. And we don't see the internals, the composition everywhere. But one of the options we discussed at the previous stop was that some of these flats are in part deltas. At least the initial surfaces are deltas. And that's been an interpretation for parts of the Great Terrace in the past. Some people have argued or interpreted it as being deltaic. But this architecture is really not what we'd expect in the delta. It doesn't have, at least for a coarse grain delta, it doesn't have the typical sort of very coarse, steep, foresets. This is largely planar.
Right.
So if you think of a river moving over the landscape, that might be more like the configuration of a deposit we'd expect from a river system or even an outwash plain. It could be a very high energy, because this is high energy transport. There's some very coarse clasts.
Let's walk up this way.
Yeah.
Get a little other shots.
When you look carefully at this, you can see that there's channel forms and there's stratification, cross stratification inside the channel forms, and then there's cutting from subsequent channels in parts behind us. If you see, there's a really sandy unit. You can actually see some cross stratification within that sandy unit.
Yeah. So
a range of processes that are probably taking place, but all, I think, pretty consistent and reasonable with a mostly fluvial deposit. You see that really well across, the planar stratification on the other side of the valley.
This is a boatload of sediment. It has to come from the north, doesn't it? What other options would you have?
Well, no, this comes from the east.
Oh, this is one of these side valleys.
I think this flat is partially, some of the sediment is derived from the east, but also perhaps some of it may well be derived from the north.
That's not a problem in Montana, right? Everybody is fine with water in Glacial Lake Missoula ultimately coming from the north.
Yeah, you're right. That way, that's the main source of water. I think it's not the only, but it's the dominant one for filling Lake Missoula multiple times. So clearly, that notion is fine there. The Sandpoil arm is also one where there's water draining southward from the southern margin of the Cordilleran ice sheet, which is actually just one drainage over from here.
Oh, really?
Yeah, the North Fork of the Sandpoil is, when we were in Tunk Valley earlier, if we kept driving, we'd have hit the North Fork of the Sandpoil.
Okay. So it's like everywhere.
Well, it seems to work other places along the southern margin. Let's just put it that way. Now you're just poking the bear.
Well, it just. Well, let's put it this way. In the next decade, especially with the new LiDAR we have, isn't this valley ripe for a re-examination?
Sure. Yeah, absolutely. But I think the story is one of, the LiDAR is fantastic and it's an immensely useful tool, but the details are going to be, I think, in the ability to make sense of these deposits.
That's why you're out here.
Yeah, in part. And then working on the timing, which will be a whole other way of constraining the time when that might happen, if we get to something coherent in terms of a story of events.
Pretty round.
Yeah, certainly. Lots of granitoids and
Thank you. Hey, thank you for your time today. It's been a blast.
My pleasure. It's always good to have other eyes on things and help think through some of these questions.